first question that we have to answer is about linearity itself. What's linear about linear algebra? What exactly does linear mean? In order to answer that, we have to take a step back and talk about variables and expressions. Because what we are trying to answer here are the conditions of linearity. When can you call something linear? So we have to define what linearity is, and also kind of define what sort of entities can be linear or non-linear. So that's why we have to start talking about variables and expressions. So let's start with variables. Variables are like a placeholder, like a container for a value. So the value can be a number. That's where we will start. Usually it can be like an integer or a real number or a complex number or something even more complicated like a mathematical object. It can be a vector or a matrix or even a tensor, a mathematical object. So that is what a variable is. It can contain something, a value. Then you can apply mathematical operations to it. Like you can add things, add two variables, or add a constant variable. You can perform divisions and multiplications, etc. So you have variables and then you have mathematical operations associated with variables. Now, if you think about it, these are not unlike the variables that you encounter in programming. So in programming, a variable is like a memory location with a label. So if you say x equal to something, or let x equal to something in, say, JavaScript, then there is a memory location allocated, and there will be a label attached to it called x, and then the value that you specify will be stored in that container. And of course, the container can contain single values or complex data structures or objects, or even functions, etc. And they also have operators. So there is a one-to-one correspondence between variables in mathematics and in computer science or in programming. Expressions are made up of variables. Any combination of variables using mathematical operations will be an expression. So you can have x by itself, x being a variable. So x is an expression also, a simple one at that. And sine x is a function of x. So that is an expression also. Of course, we haven't defined what a function is in our context, but this is a mathematical operation on x. Given x, you will get the sine value of it, or x squared e to the power x, natural logarithm of x, or a quadratic expression like ax squared plus bx plus c, etc. Those are all expressions. And if you allow yourself to have complicated variables like a vector, then a matrix multiplying a vector will be an expression on that vector also. Don't get too hung up on that yet. We will deal with that later today. The thing is, an expression will evaluate to a value. An expression in x, let's say 5x, that is an expression. And if I give you x equal to 2, then the expression will evaluate to 5 times 2, which is 10. So input 2, output 10. And we have to understand that linearity applies to expressions. Strictly speaking, it's the expressions that can be either linear or non-linear. So in defining the linearity of expressions, we are looking for two properties, just two. You scale the inputs, the output should scale. So take the expression 5x. Suppose I take the value of that expression when x equal to 2. 5 times 2, that is 10. Then suppose I double the input. Instead of taking 2, let me take 4. Then 5 times 4, that is 20. The output also doubles. So that scales. So if the input scales, the output should scale. The second condition is that the output for the sum of inputs, that is, if I take the input and split it into 2, then the output should be the sum of the outputs. Again, let me take this example, expression 5x, that is our expression. Now let's take the value of x as 3. So 5 times 3, 15, that is the value of the expression. Now the input is 3. Let me write the input as 2 plus 1. What's the output for 2? 5 times 2, that is 10. What's the output for 1? That is 5 times 1, that is 5. What's the sum of the outputs? 10 plus 5, that is 15. And what was the output for the sum, which is 3? That was 5 times 3, that is 15. So it's the same. So the output for the sum of inputs, same as the sum of the outputs. And if these two conditions are satisfied, then that particular expression is linear. So in our case, 5x is indeed a linear expression. You can verify and convince yourself that things like x squared or anything else like sine x, etc., they are not linear by these two conditions. Now let's talk about functions. A function is an expression with a name. So 5x is an expression. If I call that f of x equal to 5x, then that is a function. I'm defining a function using an expression by just calling it by a label f in this case. F of x is 5x. F of x is ax, that is an expression. Gx is equal to logarithm of x, that is another expression. Then gx is a function. F of x is equal to e to the power x, that is a definition of another function. Now, in addition to actually defining a function by assigning any random expression to a label, we require just one extra property. We require the function to be single valued. So if I say fx is equal to square root of x, then that is a function because we understand square root to give you only the positive square root. But if I write fx equal to plus or minus the square root of x, then obviously I have plus or minus, then it is not a function. So if I take x equal to 4, I can get plus 4 or minus 4. So that's not a function by our definition. It's a multi-valued function, but we require our functions to be single valued. One classic example would be an inverse trigonometric function like sine inverse of x. That is clearly not a function by our definition in our context in this course. Now, this is where our mathematical maturity idea comes to the fore. What I'm trying to say is this. For our purpose in this course, sine inverse of x is not a function. But in some other context where you want to use it for some purpose, you might want to consider that a function. You cannot go around saying at that point that, oh, prof told me 10 years ago that sine inverse is not a function, so this cannot be a function. I cannot use it that way. No, this is just a definition. It's a tool in your toolbox, a mathematical toolbox that you can use to solve the problem that you encounter. So in this case, in our context, in this linear algebra, for our purposes, I'm saying that it's not considered a function. But if you want to consider a function for whatever algorithm that you're developing for whatever reason, that's up to you. You just have to be aware of the fact that that is what you're doing and you will be fine. So the functions also are not unlike programming variables or functions. Just assigning a name to an expression that is a function, that is kind of like assigning an expression, a programming expression that is, to a name or defining a function. So this equal sign here, this is an assignment. It's an assignment. That is something to keep in mind. Now let's continue and define linearity for functions. Remember, a function is a label equal to an expression. A function of a single variable x is fx is an expression in x. So input is x, output is a value of that expression. And there's a notation that you will write f colon r. This double r here is a set of all possible real numbers, and x is a member of that. So we're using set notation, which is why we can say x is a member of r being the set of all possible real numbers. And this function f takes a value that is real and gives you a value that is real. That will be the kind of functions that we will be dealing with in this course. At least they will have real components. May not be in one dimension, but at least real. Now, linearity in this case is defined solely in terms of the linearity of the expression, which we already defined. So if it scales and the summation rule is respected, then this expression is linear. And since the linearity of the function is defined in terms of the linearity of the expression, the function whose right-hand side is that expression that is linear will be linear too. Now, let's take one more small step and think of functions as a transformation. Actually, the difference I'm trying to highlight here is a difference without too much of a distinction, because we will be using things like transformation or mapping or function, etc., to mean roughly the same thing. The transformation is something that takes one mathematical entity, a number for instance, or it could be a vector or a matrix, as input and return something else as an output. So it can take a vector and give you a number, like the size of the vector for instance, or take a more complicated thing like a matrix and it might give you one number, maybe its determinant, one mathematical entity transforming to some other mathematical entity. So you can think of a function as transforming its input to some output. like I said, this is a difference without too much of a distinction here. So x goes in and y comes out. A real number x gets mapped to another real number y through the action of fx. So that is the kind of picture. Now let's take a few examples here. A function fx takes x and then gives you mx plus c. That is a function for every x there's only one value. Here also ax squared plus bx plus c. For every x there's only one value, and so on. So those are all good functions. Then couple of counter examples. The moment you see plus or minus, that means it could be plus or minus. Hello. So two numbers corresponding to each number here. So obviously that is not a function by our definition. So sine inverse trigonometric function is not a function by our definition. Now let me give you a couple of transformations defined by these statements here. I want to collect all possible x's that will obey the rule that y square is equal to x. Does that define a function? Is it single valued? Y equal to x square is a parabola that opens upward. Y square equal to x is a parabola that opens to the right. And that's not single valued because for every x you have two values of y. Now what about y cubed equal to x? That is a shape that goes like that. That turns out to be something that defines a function. So kind of interesting to note these things. Not absolutely critical for our purpose here, but interesting nonetheless. Now after having defined functions, it becomes easier for us to actually write down the conditions of linearity more formally. So we will do that for expressions and functions because those are the things that we know. But we will say that the same thing applies for equations. We haven't defined equations yet, but we will momentarily. So what sort of objects can be linear? Expressions can be linear or nonlinear. Functions can be linear or nonlinear, and so can equations be. So an expression is linear if it satisfies two conditions, scaling and addition, as we talked about. And if the expression is linear, then the function in which it is the right-hand side is also linear. So because the linearity of a function is defined by the expression for which it stands as a label. Now an equation will have a left-hand side which is an expression, and if that left-hand side is linear, the expression in the left-hand side is linear, then that equation is linear too. So we will hold our thoughts on equations for a second, but let's define these conditions of linearity more formally here. These conditions are called homogeneity and additivity. An expression is linear if it satisfies homogeneity and additivity, both. And a function that stands in the place of an expression as a label is linear if the expression satisfies homogeneity and additivity. In other words, if the expression is linear. So homogeneity is scaling the input variable should scale the output by the same scaling factor. Now that we have defined f of x, we can say that if we scale the input x by a factor s, then the output of the function should be such that the original output for x is scaled by the same factor s. So that is critical. It scales by some random factor. Obviously, it is not linear. So homogeneity means scaling the input should scale the output by the same factor. Additivity, the output of the expression for the sum of two inputs should be the same as the sum of the outputs of the corresponding inputs. So that is easy to write down now that we have this mathematical notation. So f of x plus x prime, sum of two inputs, should be f of x, the output for the first part, plus f of x prime, the output for the second part. So that's that. The sum of inputs should transform to the sum of outputs. So that's how we define homogeneity and additivity. So if I give you anything and ask you, is this linear? You have to check these two things. Both of them have to be satisfied before you can call the expression or the corresponding function linear. Now let's talk about the implications of these conditions. These implications will form tests in a certain hierarchy, but ultimately we are actually making sure that the conditions are satisfied. The tests are like the special cases of the conditions. So scale the input by any factor, the output should scale by the same factor. Sum of inputs should produce a sum of outputs. So the input can be scaled by any factor, and 0 is a good factor. What does that mean? That means 0 should always transform to 0. So because if I take any input, say 5, multiply by 0, the input becomes 0. The output should get multiplied by 0. The output has to be 0 if the expression needs to be linear. So that is the first thing that you would do if I ask you to test something. You just put 0 everywhere, very easy. If the output is not 0, then immediately you can say that it's not linear, you don't have to do any more tests. The second thing you might want to do is to take the negative input. That is, if the first test passes, that is not enough, you have to continue. Just invert the sign of the input and see if the output also changes sign, because -1 also is a good factor. Then if that also works, then you're not completely sure because you tested only 2 cases. You cannot go from specifics to generalities. So you have to then actually scale by any factor by S, a random general factor, and then make sure that the output scales by that factor. And then of course you have to test the sum of inputs, the same sum of outputs. So what I'm giving you here are the tests in that hierarchy, because I believe this would be the easiest way to proceed, because if the test fails at any point, you don't have to do the more complicated ones that follow. So let's check a few examples. So fx equal to mx plus c. How would you test it? Just put x equal to 0. That is our first test here. X equal to 0. Then what you get is c. So this expression mx plus c is linear only if c equal to 0. So even though you learn mx plus c is a line, but it's not a linear expression in one variable, which is something interesting and something to keep in mind. Now, x bolded is my notation for a vector. So x is a vector here. And the double bar here, that is for the norm of the vector. Norm means size. So is the size of a vector a linear function? So you take a vector, give it as the input of a function, you get a number, size is a number. Is that a linear function though? So let's start with the 0 vector. So size of the 0 vector, let's say 0, 0, 0. It is 0, so that seems to survive. That is true. That is good. Then suppose I double the vector, then obviously the size doubles. That's what it means. So that also seems to be fine. So this seems to be fine. But if I take the negative of the vector, scale it by -1, size is always positive. So the length of the vector is positive. So it doesn't obey this guy. So it fails in step number 2. Now here, x square obviously is not going to be linear, but 0 transforms to 0, that is fine. Negative x doesn't transform to negative, so it fails here. fx equal to 0 unconditionally, is that linear? Okay, if I take x equal to 0, this is fine. If I take x equal to 1, that is 0. If x equal to -1, that also is 0, which is -0, so this is fine. Scale the input. I scale the input. I take x equal to 1, I get 0. Scale the input by 2, I get 2. F of 2 also is 0. So that is got the scaling factor times 0. So this also is fine. And sum of 2 inputs. I take f of 1, 0. F of 2, that also is 0. F of 1 plus f of 2, that is 0. F of 1 plus 2, which is 3, that also is 0. So this guy also is satisfied. So this is actually okay. This guy is linear. X plus 3, this is obviously not linear. This is a special case of that where c is not 0 and m is 1. So that is not linear because f of x when x equal to 0 is 3. So it fails in test number 1. Last one, f of x is x plus 3x, which is 4x. When if you actually work through this one, it is actually linear. In fact, the only linear expression in one variable turns out to be something like ax. This is the only linear expression where a is any real number. Right. So that brings us to the end of what we mean by linearity. In the next video, we will move on to equations and what we can do with equations, and this curious things about equality. Equal sign means different things to different people in different contexts.